Okay, so first we'll look at the one of sort of the popular ones, not as popular as it used to be, but still is popular. So the power BJT, or the bipolar junction transistor. So this is a fully controlled switch, meaning that we can switch it on and off anytime we want. So the control will be using the base current. So if we apply a sufficiently large base current, positive current, then it will switch on. I'm assuming everything else is biased in such a way that it switches on. So the VBE, for instance, is definitely forward biased. Then if I give it a positive current, it will switch on. If it's large enough, so we want to make sure that the current that we apply is large enough that it pushes it straight into saturation. So we don't want to hang in the active region where you have this idea of, where you have a bit of power dissipation. So we want to go straight into saturation. So we'll use a relatively large current to switch it on. And then we can either set that current to 0 or try to set it to a minus value. And then in that case, it will switch off. So the other thing we get with the power BGT is that then we can also handle a large current. So it can handle, it would definitely handle more current than the small BJTs that, for instance, you'd find trying to, in a small portable radio, something that maybe someone's using to amplify the signal from the antenna of a radio, a small radio. So that would be maybe at most a few watts or a few milliwatts. So, but in this case, we are looking at something that can handle much more power. Maybe even something that you could want to use in a power amplifier, something like a class B or class D, class A, B, class D type amplifier. Because again, in those cases, you're really doing switching. Then the other bit is that it needs to be able to block a large voltage. Remember that since these are transistors, we're using them to block positive voltages, not negative voltages. And so you never really apply negative voltage to this. Same thing with the current, that the current is also basically going in one direction. So it's a unidirectional current, and we're basically blocking a positive voltage. So we don't deal with negative voltages. Okay. So this is sort of a way to think about how this device works, a simple way. So the analogy is to think of this as a normal sort of plumbing system where you have a bunch of electrons coming in from the emitter. So the emitter is the source of the electrons. Then the base of the BJT acts like basically a tap that we can use to switch this on or off. And then we want these electrons to flow down to the collector. So I'm looking at a collector sort of as a sink or something like that. So the electrons are emitted, they come down, and then depending on, so for the first case, where the base current is less than 0, but again, remember, we're keeping VCE to a positive value. So, and we're doing that so that essentially the electrons are attracted from the emitter towards the collector. So that is why you have with that VCE being a positive value to sort of encourage the electrons to flow from the emitter to the collector. So when it's cut off, I can apply either a 0 base current or a minus value. So that's equivalent to being in cutoff region or being basically off state. Then on the other side, what we are doing is we are essentially opening the tap by applying a large base current. And then, so that's a large base current, so that we go straight into saturation as opposed to going into the active region. And then because you have this flow of electrons, which essentially means that this is now a conductor, the VC is small. So VC is basically in a saturation region. So you have a very small drop across that. So it looks more like a conductor or just a piece of wire, a copper piece of wire, for instance. So we have these emitters, these electrons coming down from the emitter and flowing all the way down into the collector. So meaning that the current is flowing the other way. As you know, that current, basically by convention, current goes from the collector to the emitter in this sort of approach. Then the other thing, as you've noticed, that I leave a little bit of the base out here to sort of indicate that there's still a bit of resistance, or the electrons don't just flow through completely. So that's the equivalent of having a small voltage drop. That unlike the ideal case where there would be no drop at all, in this case, there's still that VC is saturation. So the electrons still have some trouble even crossing this. So that's why I have a bit of that base, sort of that tap, sort of look like we're sort of doing some blocking at least, so that there's resistance. And so every time we have resistance, it means that you're going to have power dissipation. So the idea is that you have to have a heat sink, especially when you're dealing with these power devices. So you need a heat sink to basically keep this device cool, to sort of draw away the heat from the device. Otherwise, if they overheat, they fail. And you can see that the reason you have heat is because you still have a small VCE and a base current. So you have IB times VCE. Actually, it's not really IB. It's the more problematic one is a current. So the emitter current or the collector current, that gets multiplied with a VCE. So that product is basically the power that's going to be dissipated. It's the same thing on this side, that although this is closed, I've sort of shown it as closed. You still have a little bit of current that sneaks in. That's so-called, you remember, the bit of leakage currents. So even in this case, even with cutoff, there's a bit of power dissipation. It's much smaller than the kind of dissipation you'd find when the device is operating, when it's on or in saturation region. So make sure you have a heat sink, especially when you're working with these devices, with the power devices. All of them, even the diodes, so they all dissipate power. Not as much as some other cases, but there's always power dissipation because you're dealing with large amounts of current. Okay, I hope this sort of analogy is good, sort of is clear. So, are there any questions on this before we sort of add a bit of complexity to this? You'll notice that there are no holes, and yes, yes, you had a question? Okay. Okay, maybe so. So basically, what is one reason to actually not show the holes is that the truth is all the charge, the only thing that's really in practice, that is really moving the charges around is our electrons. So we talk about holes, but holes are sort of, we talk about holes, but at the end of the day, it's really electrons that are moving up and down. So, so that's why I don't need to actually indicate the holes in this case. Okay, so let's look at this structure. Again, this is a power BJT. So we have this slightly doped region. So we don't have just a PN, a normal PN sort of junction out here. We have a lightly doped area. So remember we said that with this, because it has just a few electrons, it's slightly doped. So the concentration of electrons in the N minus area is less than the concentration out here in the N plus area. And we're doing this so that this looks more like an insulator than this region or these other regions. And the reason for doing that, is to enable us to block large voltages. So without this, would not be able to really block large voltages. Again, remember, we're blocking positive voltages in this case. But so this is sort of what distinguishes it from, okay, this among the things that distinguishes it from what we call a signal BJT, something you'd use for maybe in communication system or something like that. Small portable, whatever, small portable radio, something like that, to do simple class A type amplification. So you have that region, so it has to be lightly doped and it has to be relatively large. So the blocking voltage, which is the voltage basically before this breaks down, is directly proportional to the width. So the wider this is, then the more that sort of increases its ability to block. So the breakdown, so I'll call it a breakdown voltage, is proportional to the width and also inversely proportional to the concentration, meaning that it should be, if you want to block a large voltage, this has to be to have a low concentration, so low doping, and it has to be wide. Then the other bit is that we have this vertical structure, and we'll see for all these transistors, we have a vertical structure. And what the vertical structure does is to basically enable this device, it gives it more of a surface area so it can carry more current. So you need to be able to carry more current to really say that you're talking about a power BJT, or we'll see something with other devices. So we have the vertical structure, we have a wide, lightly doped area. We're blocking positive voltages. And then as you can see, that this is just the side view. If you look at the top view, you will see that actually it's as if I've got a bunch of the kind of, not really paro, but sort of paro BJTs connected together. So the device itself contains a bunch of sections of it's like I have several BJTs. I don't want to really say that in parallel. Okay, we can say it's parallel, although that creates some issues. So this also makes it easier to carry significantly more current than a signal BJT. So you can see that the base terminals are connected, and then I've not shown it, but the emitter, the different emitters will also be connected, sorry. And then at the bottom, you'd have, so I didn't show that, but at the bottom, you'd have a collector also connected. So instead of really thinking about this as a single BJT, within the package, you have a bunch of them. And this is one of the reasons you can have a lot more current flowing through your system, as well as the fact that, of course, a vertical structure. If you're looking at a regular BJT, then you'd have the emitter, you'd have the base, and then you'd have the collector out here this other side. So everything would be lateral. So you'd have sort of a lateral design. The collector would be out here. So that's another difference that you should notice with this device. So sort of think about how this works. Let's say, okay, I need to sort of change. Let's see. So we can look at, let's see. Okay, so anyway, so for cutoff, I actually don't need to do so. Cutoff is really have this as more or less reverse biased. So for that, I can talk based on this. Okay, no. Yes, I'll share something. I'll go to Microsoft Paint. Okay, what's that? Okay, I thought I had the budget. I'm looking for my budget, the budget. I've got it here on my system somewhere. So, okay. Budget is I've got a structure there. I've got another one. Okay, so it normally works better when I look at let's see. When I do this in Paint, I've got a I guess it's called a tablet. Works better when it's in Paint. Okay. So let's try to share Paint. I hope it does. I hope I can draw. So share Paint. Okay, Paint is over there. Okay, I hope you can see Paint. I've got Microsoft Paint up there. So I'm sort of going to try to show what this is like. So basically, we said we need to do a connection between the collector. So I'll have, let's see, so I can have, so I want to run this through a load. So I'll have some kind of resistor out there. Connect the resistor. So the resistor is basically what I'm using as a load. And then connect it to another source. Okay. And then I'll have that as plus minus, and then ground that side. So that's my VCC. So that's my source. So I can still leave that as a positive. I can simplify this by sort of grounding the emitter. How does that also sort of grounded? So there's a connection between it's VCE positive. So basically what I'm doing is to setting VCE to be greater than 0. And I said the idea behind this is to make sure that any electrons move from the emitter down to the collector. So that's why I'm doing this. VCE to that to be greater than 0. Then, so that's why I am applying that. So I'll have, then, so we'll basically look at the base. So this is, the base is our control. So I can have this be maybe, okay, it needs to go through some kind of resistor to at least simulate. So this is going to act as my current source. So if I've got a base current, remember I said, okay, if I have a base current of say less or equal to 0, then I should change colors. So let's use red. So in this case, although I have a bunch of electrons in the emitter, then these electrons cannot cross to basically come down to, they'll not be able to cross that PN junction and sort of come down to the collector. So because of the base, so this is reverse biased. So I've got VBE being reverse biased. So that is basically if we are talking about cutoff. So this, although I'm keeping VCE as positive, that BE is reverse biased. So there's no current flowing. So our switch is basically open. Remember, another way to sort of think about this is, okay, I can redraw it here. So, so what we're really doing is we're using our base. So the base is the control, and we have electrons from the emitter. So think about it as a pipe. You say as a pipe of a pipe. Well, basically these electrons would want that electrons to flow down from the emitter to the collector. So by reverse biasing, I'm essentially keeping this closed. So since it's closed, no electrons will be able to flow down to the collector. So that's basically our cutoff. So we are within the cutoff region. So this one's obviously the easiest one to think about, that I basically don't even have to do anything with a base for this device to be off. Then the other case, which is sort of the more interesting one, is a case where we want to run into saturation. So I'm going to try to see if I can clean this up by doing this. It's relative. So we're going to look at forward biasing. That's the best I can do. Okay, so get rid of this stuff. So, okay, so basically, now if I want the electrons to flow, again, eventually, this of course is something you've seen before. So I won't spend maybe as much time on it as I should. Okay, clean up a little bit. So to forward bias, need a pen. So to talk about this being on, so on state. So for on state, I want basically saturation. And we say the reason I want saturation is because this VCE becomes a small value, so that I have VCE sat is greater than 0, so but it's a smallish value. I won't put it at 0 because 0 sort of it's greater than 0. So basically, in this case, to get into saturation, I need a large base current. So IB is greater than 0, it's going to be relatively large. So to push it directly into saturation. So basically what is happening is that now, if I get this to become forward biased, then I can have electrons flowing from the emitter and crossing this boundary. And you remember, for basically these devices, that boundary is designed to be small enough that in addition to being attracted this way, most of them will actually, because that gap is small, will be attracted down here. So I'll have a bunch of electrons coming down, attracted down into this region. So we have charges being carried by electrons as well as a bunch of holes. So because you have that P. So internally, I've got a bunch of holes. So it's why it's bipolar. So I can say I've got holes and I've got electrons. So, but mainly what is happening is that these electrons are flowing down this way. So from the emitter down into the collector. So I've got several of them. So if this is in saturation, then I've got very many. So this resistance, the resistance in the lightly end in this region has been reduced significantly by the presence of holes and also the presence of these other electrons. So they are significantly more charge carriers, so holes and electrons that can carry charge from the emitter down into the collector. So I have a lot of current flowing down. So you still have some resistance because the resistance never really goes away. But you have a lot of current flowing down there. And so, which basically means I've got current. So let's see, so it means I've got current flowing. Current has to be flowing in that sort of the other direction. So I've got a collector current. Again, sort of simplify, I'll say that the collector current is roughly equal to the emitter current. So for most of these cases, we'll sort of be doing this approximation. So that I just talk about the collector current instead of talking about the emitter current, because I'm assuming that they're both roughly the same. So the only difference, like I said, is this large, lightly doped area. And it's actually meant to come in when we are blocking. So when we're doing reverse biasing, when it's off. But when it's on, then it's not as important. Although because it's slightly doped, what that means is that the VC is sat down here. So this value is going to be higher. This is 0.6. I don't have a number for this. But VC is sat for a power budget is going to be higher than the VC sat. VC is sat for a signal budget here. So it's another thing to remember, that the voltage drop is going to be greater, and mainly because you have the slightly doped area at N minus. So you're going to have a bit of a larger voltage drop, but because now you're able to block a much larger voltage when it's in cutoff, then we can take that sort of as a benefit. So we can do that trade-off that, yeah, this will be larger in terms of blocking, of dropping when the switch is on, when it's in saturation. But we're able to block much larger voltages. So that's sort of a trade-off. There's always trade-off with almost everything we do. We have to sacrifice something to get the benefits. So since this is something you've definitely seen before, I'm not spending as much time on it. So the other bit is that this saturation for the BJT is a bit sort of split into two. But let's go back to the slides first, then we'll talk about that. So I'm going to stop sharing the paint and go to the slides again. Okay. So I can find, okay, there it is. So, so share. Okay, there it is. Okay, so we're back to the slides. So this is sort of, let's run it. Current slide. Okay, so this is a symbol. So we're doing NPN, and NPN, we always talk about NPN, sort of easier. Most of us are used to the NPN. So this is a resistor. That's basically our load. And then, so when it's forward biased, I've got this current coming down. But this current is positive. So if I push it into saturation, then everything's going to be forward biased. So I can have a large amount of current, collector current flowing down into the emitter. So I'm using a pulse to switch this on. Another thing to remember is that this current has to be applied continuously. So it's a current-driven device, but for this to be on, we have to apply a large current all the time. So for as long as we want this to stay on, the current must be applied. So that's one of the weaknesses of this device. So we have to supply this current. So we have a large current flowing in here all the time to keep this on. So we'll say that there's another device that sort of solves this problem for us, where we don't have to maintain this current. Okay. So when we look at the IV characteristic, so current voltage characteristics for a power BJT, then a bit of this, this diagram doesn't really do a good job. I've got another one somewhere. So in Ned Mohan, what Ned Mohan shows is that the saturation region actually for the BJT is split into two regions. So there's something called a quasi saturation and then hard saturation. So hard saturation is what would normally think about when we are thinking about saturation, normal saturation. So with hard saturation, then the VCE saturation voltage would be very small, would be out here, and then would have a large current flowing. And then there's the other bit of called hard saturation, sorry, quasi saturation. We still have a lot of current, but the collector, the VCE sat is a bit higher also. So the VCE is a bit higher than in the case for hard saturation. So this saturation sort of split into two. The benefit that comes, so you can operate in sort of both regions. That with a hard saturation, the difference means okay, I've got a bunch of people. Okay, who else? Okay. So the sort of difference between the two, the sort of the two saturation regions is that hard saturation, then I have a large current, a real large current, and a very small voltage drop. So VCE sat is small. Then I said there's something called quasi-saturation here. So quasi is sort of in between. Then in that case also the VCE saturation is relatively small, but still larger than what you get for hard saturation. And then so the difference basically comes down to when you're doing the switching. Because remember, to switch from one state to another, you have to go from, so if I want to switch off, then I need to clear out, so let's see if I can, I don't want to go back to, so. Okay, so if this is sort of the off state as it is, so to go from on state, so you remember with on state, we had a whole bunch of electrons. I've got a whole bunch of electrons flowing from the emitter down to the collector. I've got a whole bunch of holes. So to switch off, I need to get rid of all those other extra electrons that are flowing, as well as the holes. So that basically I can go back to a situation that is sort of like this. So I need to clear out any holes and electrons, extra electrons from this region. So it takes a certain amount of time to be able to clear this out. So the more current I have flowing, so if I'm in hard saturation, it means I've got a lot more electrons in this region. So to switch it off, I've got a lot more electrons to sort of get rid of, to sort of recombine so that I can set up a new depletion region, which is what you have for when you're switched off or you're in cutoff region. So I would need to get rid of those extra electrons in here. And so that takes time. On the other hand, if I'm in the quasi-saturation, then it's not fully on, so I don't have as many electrons in here, which means I have fewer to get rid of, which basically will mean that that would take a bit, won't take as much time. So that's sort of one way to think about it. A simple way to think about it, that to just switch it off. So if it's easier, so it's faster to switch off from quasi-saturation to cutoff than it is to go from hard saturation, which has more current and more electrons than. So hard saturation, it takes longer to switch off. And basically, what you can, so depending on your application, it means that if I want to be able to switch off quickly, then very quickly, then quasi-saturation is better. But if I really want to have significantly more current flowing, then I would sort of want to go into the hard saturation. It's kind of a way to think about it. So it's why sometimes you'll see that depending on the application, both of those approaches. So you'll pick one of the two approaches, sort of based on what your application is. So if the idea is to switch very quickly, so also there are some applications where you need to be able to switch on and off very quickly, and the applications where you don't have, the switching doesn't have to be as fast. So there are some cases where you're controlling things where you can, let's say like what? Okay, maybe not for it, but if you are doing things like rectification or that kind of thing, then the switching, that it can take longer to switch. So you don't really care about the switching. You can be switching much more slowly if you're looking at things like rectification, as opposed to, we'll look at some other things that you can do where you really need to be able to switch very quickly. Then this device also suffers from something called secondary breakdown. So I'm going to leave it up to you to sort of go and look up these things. So I'm going to put that in the homework. So assignment, as a way to force you to sort of read up on some of these things. So secondary breakdown, conductivity modulation, then the two saturations, hard saturation and quasi-saturation. So that's a good way to do it. So you'll have something to do from the assignment. You sort of have to look at a bit of the device physics. Okay, so moving on. So because of those issues, the Power BJT is sort of falling out of favor. So it's not as common, especially in this sort of switching applications. But we still sort of talk about it because the way it sort of acts. So we take some of the advantages it has, and then we transfer them to essentially the power MOSFET. So we'll see there's this one device, the IGBT. We'll see that it has some benefits. So you take a combination of the BJT and MOSFET. So you take the good things from the BJT and the good things from the MOSFET. And then you create this IGBT, which is what the more common sort of device that is used. So that's why I want to sort of do a bit of a review on BJT, so that when we do that combination, it becomes a bit easier to understand. But okay, so first we need to go back to the MOSFET. So the difference with the MOSFET now is that mainly, the switching, we'll say that the switching is going to be faster. So anytime you want to switch from on to off or off to on quickly, the power MOSFET will do a better job than the BJT. It also is fully controlled, meaning that we can switch it on and off. We'll see that the control is actually better because it's voltage controlled. So voltage control is much easier than current control. It's easier and therefore generally a bit cheaper. So controlling, but it's a fully controlled switch also. Then it has large current carrying capability and large voltage blocking. Again, like all the transistors, like the BJT, we are blocking a positive voltage. So VCE never becomes negative. So what we're blocking, it's not called VCE. It's not called VCE, sorry. But we're blocking a large positive voltage, and we need to be able to carry a large current. So, let's see. So we can still have something sort of similar to what we had before. So a sort of analogy. Again, remember we said, okay, we can sort of think of this as a pipe. So you can see one of the things that has changed is the names have sort of changed. So instead of saying an emitter, now we are calling it a source. Instead of calling it a collector, we are calling it a drain. So drain is sort of the American version of a sink. So it's basically a sink, but still maintain that drain. The Americans invented most of this stuff, so they use the American English. So this basically sort of like a sink. Okay, drain. So source, drain, and then instead of a base, we have a gate. So we have this control. So again, we are controlling electrons that are coming from the source and want to go down into the drain. So we've got this sort of tap device, which we are calling a gate. And then again, I've got this drain to source. So drain to source, I'm making it positive so that basically the electrons flow from the source to the drain. Because if this was zero, then there would be no reason without that potential difference, there's no point for the electrons to flow from the source to the drain. They'll just stay where they are. So we need a bit of this. Then, so for this state, again, we have a case where this is cutoff. So cutoff region, so when the switch is off. And so the control is based on this gate source. So voltage, the gate VGS is less than a particular threshold. So this threshold is some positive, it's a positive voltage. So this is a voltage control device. So as long as VGS is less than a certain positive voltage, so the manufacturer will tell you exactly what this value should be. So based on that for that particular device, so as long as it's less than this threshold, this device is going to stay off. So you won't have any current flowing from the drain to the source, or basically electrons from the source to the drain. So this, again, this is sort of a simple situation. Then, so this is the off state. So for the on state, again, that sort of the names kind of change. Sometimes it's called triode. I think it's also called ohmic, or I forget what the other name is. So we'll go with triode. So for this case, again, we want it to be fully on. And again, the reason we always want it to be fully on is so that we reduce the power dissipation. So we really, the most important thing is to reduce power dissipation. So if it's fully on, then it has a very small resistance. So for MOSFETs, normally we talk about RDS on, so resistance when it's on. So we want that to be relatively small. So the condition for this is, we've seen that VDS is greater than 0, but also want VGS to be greater than that combination of VDS plus V threshold. So this is sort of the condition for this to be fully on. Then when it's fully on, so you have a large amount of electrons flowing from the source to the drain, which means that you have a lot of current flowing from the drain to the source. And as I did before, I leave a bit of this, of that tap sort of to show that there is resistance. There's still some resistance. So because there's resistance to the electron flow, that means there's a voltage drop. So when the switch is on, there's still a voltage drop. So you have VDS greater than 0, but also you have a large current. So you have power dissipation. So you've got a current and you've got a voltage. Or for MOSFETs, we normally talk about RDS on. So for that reason, you're going to have heat. And so again, because you're going to have heat, you need a heat sink. So maybe a piece of aluminum with fins, or you can have, or in addition to that, in addition to the heat sink, you may have a fan running. So just to make sure that this sort of it keeps cool, because if it overheats, then it will fail. So we want to make sure that we find a way of cooling it so that it doesn't fail. Okay. Okay, so that's sort of the analogy. So let's look at a real device, that's sort of the structure. So when we look at the structure again, you'll notice, you'll notice that we have this, and this came from the Semicron, what is it called? Semicron something. The Semicron manual, it's an application manual. So you should download this. I hope you've already downloaded this. The only thing I added was basically this thing called a power diode. I added it to that symbol because they don't have it, but I mean, it's there, you need to be aware of it. So the difference again is this thick layer of a lightly doped N. So this is N minus, that's the subscript is a minus, the superscript is a minus. And down here you have this thin layer where basically the subscript is a plus. So at the bottom, I have high concentration, so high doping, and then this other larger area is really lightly doped. So again, we say the light doping and the thickness is meant to help you block a really large positive voltage. So for this, I think I need to draw something. Okay, we'll have to go back to paint so that you can sort of get a feel for how this works. So, but when it's off, so to be okay, let's shift to something simpler. But again, it's a review since you've done this. Oh, the other bit is it's a vertical structure. You can still see that we have that vertical structure. So we have the source at the top, and then the drain is down here at the bottom. So we need a vertical structure. We say that's good for current flow. But let's go to paint, then sort of do a review of how this field effect works. Okay, so I'll stop sharing and then I'll open up my paint program. I need a new one. Let's see. So I'll have to draw something totally new. Okay, let's see. Just a minute. So we're going to look at the MOSFET first, the MOS capacitor. It's called MOS capacitor. So find a nice diagram of the MOS capacitor. Okay, I'm going to try to draw it. So that the drawing won't be as good, but okay. Well, let's see, where is it? That's my share. So I'm going to share paint. Okay, and title. Okay, so there's a paint. So I'll just okay. Okay. So I've got a contact. So this contact is something like aluminium. So, and then this is what I'm calling sort of the gate. So it's a metallic contact, so it's a good conductor. Then I've got a slab of an insulator, so something like silicon dioxide. So this is an insulator. And then, so we'll be dealing with a P since it really is P. So I've got a P layer. So P is highly doped. This is silicon. And so I'm going to, so for this case, I'm going to do that connect. We're going to really just look at one case. So we'll just be inverting this. So I've got plus and minus. So I've got VG. So we're going to be, I'm going to just focus on switching this on. So basically, let's change colors. We'll go with red. So since I've got a positive on that side, let's see. So we'll just sort of keep increasing the voltage. So initially I've got a sort of small positive voltage. Since there's an insulator in between, we don't really expect any sort of current or flow. So what this does is this positive will sort of induce a small negative on the side. Another way to think about it is that the holes are sort of repelled. So I've got holes being repelled and sort of leaving a bunch of electrons. So negative ions. I guess I can call them negative ions. So I've got sort of like negative ions out here. Just a very thin layer of that. And then as I keep increasing, so keep increasing the voltage on this side, eventually, so basically I've got sort of like a small depletion region. So kind of small depletion region. So as I keep increasing the strength, so this becomes more and more positive, then eventually I'll create a bunch of electrons in this layer, just a few electrons. So then we end up with some electrons. So we're talking about mobile electrons. So we need the mobile electron. The ions are fixed, so the ions can't carry any charge. So they don't move because they're fixed. But to be able to carry that charge, we need something that is mobile, or which is another way to think about it, free electrons. So we need free electrons. So as I increase this, then basically we start to get some electrons in here. So we create an electron and we create sort of, okay, let me call that a hole. So the holes, so we get a combination of the two, then the holes will disappear into here. So I've got holes disappearing in down here, and then the electrons staying. So the effect of this is to basically create a thin layer. So I'm going to draw it all that way. So I've got a thin layer of electrons, very thin layer of electrons, free electrons out here. So as long as I maintain this large, so basically that VG is greater than a particular threshold, then I'll have a bunch of holes, a bunch of electrons in here. So a bunch of free electrons, a thin layer of electrons up here. So what I've done is basically I've inverted that P layer, and it's sort of, it looks kind of like an N layer. So we've gone through that so-called inversion. So inversion, so that although this basically should all be a P, that top bit has a bit of electrons in there. And so for the simple, not simple, sorry, so basically, if I was looking at a loss signal, so the way they create the loss signal transistors is I would connect, say, N plus on this side. So I'll connect the source this side, and then connect the drain this side. So that way I've got this small channel through which electrons can flow. So I've got this small conductor through which electrons are flowing from the source to the drain. So, but this would be for the case. So this is what I want to do. And this is a situation for the low signal MOSFETs. So we've seen with the other one, with a power MOSFET, so this side will be lightly doped, but at least you see that you can see what you're trying to do. And I'm assuming you've seen this before, so I don't actually have to spend as much. It's more of a review since you've seen this before. So I create this thin channel through which electrons can flow. And the benefit of this, the reason this can switch very quickly, is that as soon as I remove this VGS, so if I set VGS, okay, so this VG, if it now becomes negative, or less than 0, for instance, or less than that particular threshold actually, then this channel will disappear. And so the effect of that is I can switch it off much faster than I did with the BJT. So that's why the MOSFET is faster than BJT. So faster in terms of switching speed. So the switching is faster. So I can switch it off much faster because all I have to do is get rid of this channel. And it's much easier it takes a shorter time to get rid of that channel. I hope this makes sense, but it's something you've sort of seen So some of the benefits we are getting is that faster switching. But then we've got a channel, we've got just sort of a channel going through this. Now that is when it's fully on. And so we said we want to do fully on or fully off. So to switch it off, just get rid of the channel, and we get rid of the channel by making this VG less than that threshold. Okay, so I'm assuming that this is clear since I don't see any hands up. Okay, so again, I'm going to switch and we'll go. So we'll go back to the slides. Okay, so where are the slides? I think that's the one. Okay, so we're back to no. Let's actually no. Let's stay with a paint. I just have to get a different version of this. Sorry. Paint is easier. So I'm just looking for a file. Power MOSFET. Okay, wrong directory. Power MOSFET. Yeah, this one I do have. Open it up in Paint. Okay. Get rid of the untitled one. Okay. So let's share the. I'm going to share this one. I'm going to share the Paint. It's easier for me to write on the Paint program to do any kind of drawing. If I try to do it with a slide, it's sort of no, doesn't look good, doesn't work out well. So this is a power MOSFET. That's a structure. I hope everybody can see this. Power MOSFET. Again, this came from the semicron hand application manual. So you can see that we have, let's look at that. Let's go back to red. So again, so this is figure 2.42. So get your semicron, so you can look at your semicron book or handbook. So power MOSFET with vertical structure, we said it needs to be a vertical structure to give it a large enough surface area. So if we're going to look at large currents, then we want this kind of structure. So for this case, it's on. So again, we'll see that we have a gate. So we say that gate is metallic, so that could be aluminum. So let's AL. So it's a metal. It's surrounded by an insulator. So silicon dioxide, that's an insulator. So that's our gate. Then we have aluminum. We have this other aluminum contact right on top. And then, so that's the contact for the source. Again, you can see there are several sources, meaning that, as we saw with the case of the power BJT, there are actually several of these sort of smaller MOSFETs that are connected in parallel. So if you look at a single package of a MOSFET, so you're looking at a single package, but it's really made up of a whole bunch of smaller MOSFETs. So it's something you've seen. So that way I can get sort of more current from the same package. So we have an aluminum contact, and then the gate is, of course, is separated from the source contact partly with this silicon dioxide. So there's no connection there. So, but the actual source is down here. So you can see that the source is really that N plus. So I've got a source. Okay, that N. So this N plus, that's going to be the source of our electrons. Then I've got this P region, and then I've got that drain down here. So I've got a vertical structure. So you remember what I said about the what we saw before, that if we're looking at the smaller signal ones, then I would have a source there, I would have the drain here, and then in the middle I would have the channel. So it'd be lateral, but this is not lateral. This is a vertical structure. So that's the difference between, so if I had to ask some of the differences you'd see between these two, that this would be one of them. It's a vertical structure. So basically I want electrons to be able to flow from the source, so go through this P region and then go down and go down into the drain. And obviously they can't cross because this is reverse biased basically, so they cannot cross. And so what was done before when we're looking at the MOS capacitor, so remember I just showed the MOS capacitor, the idea is basically to create a channel. So that line basically shows where we'll create that channel. So I want to create a channel so that I can connect the drain, which is that way, with this source. So we create this small channel that has a few electrons, and that will create that connection so that the electrons can now flow down like that. So to create that channel, we still have, you remember what we said, so we want that VGS to be greater than VDS plus a particular threshold. So I've got VDS. Okay. So we have to invert that area, that small area. So we invert it and create a channel through which the electrons can flow down and be collected. And so the current, of course, as we said, goes the other way. So that's why I sort of drew that sort of a reminder of how we create that channel. So that channel will be there as long as this is true. Remember, this VDS is a positive value. So I've got, I can throw a load here. So a resistor, and then have, I'll call it VDD. So a positive VDD on this side, a resistor to act as a load, but also to control the amount of current flowing through this device. So I'll have a drain current, so ID, so drain current flowing down from VDD and ending up down in the source. So, and that means that I have, so if you have electrons flowing from source to drain, it means I've got current going the other way by convention. So this is sort of a situation. I've got VDD there. So I've got a drain, VD is there, that's a drain terminal. I generally prefer to use this symbol. That's why I sort of ignored this one, although it's also accurate, but I prefer to use this one. I like this one better. So there's nothing special about it, just I prefer this symbol. So the other bit is that, okay, so that bit is then, okay, so what else can we say about this? So you've noticed that I basically, I've got that P, I've got, this is N plus. So we've got a P, we've got N plus, and down here I've got an N. So NPN. So technically this would be a BJT, an NPN BJT. So NPN, so this, so initially when they were building these devices, they would get sort of problems. So the device would act in unexpected way until they figured out that basically you have this NPN, you have a BJT inside your MOSFET. So sometimes this BJT would switch on accidentally. So then that would mess up everything if you have an NPN switching on. So basically what was done was to sort of short this. So you have a way to short the N and the P. So then if you short the N and the P, then this is no longer BJT. So, and you short them, you can see this is the short. So I've got this aluminum. So the aluminum is connecting the P to the N. So there's a bit of that short. So this contact is the same as that contacts. So that's aluminum. So the effect of having this is basically to make sure that this is not a BJT, to get rid of the BJT, which, like I said, historically, when they were first building these devices, this BJT would switch on every now and then, and that would create problems for you. So you short it by having this aluminum contact. So you can see it's connecting the P and the N. Same thing out here. You can see that so-called metallic contact between the N and P using that aluminum. So that's meant to make sure that since now there's a contact, then this is no longer really an NPN. But of course, you can see that the PN remains. So you have this PN junction. So the PN junction, basically what it's doing, it means that although I've gotten rid of the BJT, I still have a diode. So a diode within the body of the device. So that's where this diode comes from, so-called body diode. So this diode that I've drawn is internal. So it's part of the MOSFET. So it's why I added it, that this is an internal diode. So this is part of the device internally. So which means that this is actually a bidirectional current. You have current can flow in two directions, right? So you can have current going from the drain down to the source, but you could also have current flowing from the source to the drain. So if this is forward biased, if this gets forward biased, then you can have current flowing from the source to the drain. They can't happen at the same time, obviously, but so if you wanted, you could use this to carry current. So you can have current going that way, you can have current going that way. So this is sort of unique with a power MOSFET, that you can have current going both ways. So it's bidirectional current flow. So remember that. So at that junction, so which means, so if I've got a diode there, then when this is forward biased, then I can have current going that way. So this current going that way means I've got electrons going that way. So you got that. So that's it's called a body diode. So it's internal. So you'll see this drawn. Then, as you can see, so this is a bipolar device. So remember, with bipolar devices where you have holes and electrons, the switching is slower. So it switches on and off. It has a lower speed, basically, which means that this body diode also, switching it on and off would take a bit longer. So if you really wanted to do this, then you could install an external so-called fast recovery diode, but that would have to be an external device, external to your actual device. Okay, I've talked about a whole bunch of things. So any questions? I can ask. Okay, nothing in the chat. And I ask, okay, Suga seems to be on already. So Suga Richard, does this make sense? Or Timothy? Any questions on this? Okay, I think those seem to be on accidentally, something. Okay, I'll mute them since that. Okay, yes, Emilio. Okay.
Okay.
Yes.
So there is something I would like to know, Dr.
Yes.
You talked of the purpose of aluminum metal to get rid of the inbuilt NPN BJT.
Yes.
Then, if we get rid of the inbuilt NPN BJT, it means we are now creating the PN diode.
Yes.
So if we create the PN diode, it means a diode conducts current in one direction. And then yet these MOSFETs are bidirection. These MOSFETs are bidirection. So I'm kind of confused. How come they are bidirection, yet by shorting the N and P, we create PN diode, which by default, diode is conducting in one direction. So I'm stuck there.
Okay. It's a good question. So basically the difference is the direction. So again, if we go back to just a minute. So what is happening is, look at the direction of the current. So if we look at the normal MOSFET, the flow, so the electrons are flowing from the source and then they're coming down to the drain. So this is a main MOSFET current. So I'll call this positive current flow. So I'll call this positive direction, not current flow, sorry. So the electrons are flowing down from the source to the drain, which means by convention, so we talk about a convention, we say that the current is flowing the other way. So current is flowing from the drain to the source. So remember, that's a convention we use. So that's the direction of the electrons. They're flowing down like that. Then, on the other hand, when we look at the diode current can't flow the other way. So for the diode, the current has to flow. So for the diode, that's your anode and that's your cathode. And so current actually flows in the opposite direction. So the electrons in this case are flowing from the N into the P. So that the direction of the electrons is opposite. So for that diode, when we think about that diode, the direction, so okay, I can look at this is cleaner. And I'll just change, let's make it green. Let's make that green. So if this junction's forward biased, so if I forward bias this junction, then what is happening is that the electrons will flow. So this is the largest source of electrons, the N. So they'll flow from the drain into the P region. So now you have electrons flowing that way. So you have, remember this is shorted, so there's no problem. So you'll have electrons flowing in that direction. So the electrons are actually flowing from the drain to the source. So you see that this is, I want to call this a minus direction. So you have these electrons flowing that way. And this is equivalent to, so if we go back to, let me open this up. So you can see that for this actually to happen, it means so the current will flow from the source. The current is flowing from the source to the drain. So it means I need to do something about the way I'm doing the biasing. So the source has to become more positive than the drain. So that way I can have current flowing through the diode in that direction. So normally when we look at transistors, current flows from the drain to the source. So, and that's what is indicated. So semicron, that's all they indicated, was that current flowing from the drain. Let's see. So that's how you get that too. So this side is basically, this is our diode current flowing from N to P that way. So from drain to source, sorry, current flowing from source to drain, which is sort of the opposite, but it's the electrons going that way. Is that clear, by the way? Emilio and everybody else, because this is something that that's something that would definitely cause confusion. So Emilio, is that clear?
Maybe I will understand it. Not as such. Maybe I will understand it after to the recording we have.
Okay, okay. Okay, but okay, mainly, so you can see the direction of the electrons changes. That's a difference. So for the green, so what I've written as green, the electrons are flowing from the drain and they're going to the source. So that's the one with the diode. So which means that basically the drain, so if the electrons are flowing that way, then the current is going the other way. So it means the source has to be at a higher potential than the drain. So that will sort of be the opposite. Then for normal MOSFET action, the electrons are flowing from the source and going down to the drain. So the current is flowing the other way. So the only thing that is changing is the direction. But again, like I said, this doesn't happen at the same time because when the normal transistor is on, so that when I think about the transistor, so when this transistor is on, then so it means that the drain, the voltage at the drain is greater than the voltage at the source, then automatically that reverse biases this diode. So this diode would definitely be off. Automatically it would be off. And then you can have current flowing. So to switch, one way to basically switch this transistor off would be to reverse bias it. So if it's reverse biased, then if the transistor side, so if the source is more positive than the drain side, which forward biases the body diode, then you can't have the main transistor on. That will be off. It will be in cutoff. Okay, but as you said, you'll watch the recording, and I need to figure out how to get the recording to you. But okay, it's recorded. So that's a MOSFET. So you can have current flowing in two directions. Okay, so let's go back to the slides. So I'm going to stop sharing the paint and go back to, let's share the slides. Now, that's assuming I can find the right one. Okay, yeah. So there it is. So that's our MOSFET. So I hope you can all see it. So because I've switched. So then these are the IV characteristics. So current voltage. So it's VDS and VDS on this side and ID. So in this case, we're talking about a drain current. And we're controlling it with VGS. So this is not very clear, but again, This is from, even this is from the semicron manual. So we should look at the manual. You'll have a bit clearer definitely with the manual. So what we said is either we're doing cutoff, and again, you can realize that although for cutoff, the current is 0, we have a 0 drain current, but we are blocking a positive voltage. So that's why they call it forward blocking. So forward basically represents a positive. So it's not reverse blocking, it's forward blocking. So we're blocking a positive voltage, and then the current is 0. That's when VGS is less than a particular threshold. Then when we have that VGS greater than that combination, so we can change this so that now it forward biases. And sorry, not forward biases. So when we're in the ohmic or triode region, then we'll have a large amount of current flowing with just a small VDS, so that the voltage drop when it's on is really small, and we have a large amount of current. So we want to operate in this too. We don't want to operate in the sort of active region out here, because then you'll have a large voltage, a large VDS and a large current. And the combination of that means we'll have a lot of power being dissipated. So we want to reduce, so when it's on, we want this VCE to be really small. So not VCE, sorry. We want the VDS to be a small value. So we want to operate in this region. So that's the situation. Then, as we said, we can sort of have this negative bit also because we have a body diode in there. So we can sort of have a situation where I have this negative. But it's a PN, so it's going to be slower. It's a bipolar diode, so it'll be a bit slow. Then, of course, you have the usual limits. The VDS can't be, if the VDS is too big, then this device will break, meaning that there's a limit to how large a voltage you can block. So, I mean, you're not going to get any power diode and apply 1 kilovolt to it. Chances are if you apply 1 kilovolt, it will fail. So it will go down into avalanche breakdown. Same thing, of course, happens on the negative side also. So if the negative voltage is too big, it will still break down. It will fail. Okay, so cool. I'm sort of speeding through this because I want to get to the IGBT. So mainly because, so you have a bunch of issues with a BJT and with a MOSFET. So one idea is to have this one was to come up with this one device that would take the benefits of both. So one of the issues we have with a MOSFET, for instance, if you look at a MOSFET, was that it was a unipolar device. So for one, we didn't have that much current. So the maximum current it could carry was lower than that for the BJT, because we just had a bunch of electrons carrying all the charge. We didn't have any holes. So it can't carry as much current. Then, so BJT would be able to handle more current. The BJT would be able to carry more current. So, but the BJT has secondary breakdown, and it's also slower when it comes to switching. So to get the benefits of fast switching from the MOSFET and large current carrying capability from the BJT, this sort of device, and also to get rid of the problem of secondary breakdown, which is the device basically when it's conducting it, it can overheat. So you have the so-called thermal runaway. So it overheats and fails. So we sort of look for a combination, a device that can take the benefits of both. So we have a device, a transistor called an insulated gate bipolar transistor. So it's a bipolar device. So it means you're going to have holes and you're going to have electrons. So the bipolar coming from the BJT is fully controlled. It's fast switching. So by fast switching, I mean it switches on and off faster than a BJT. It's not necessarily faster than a MOSFET, an equivalent MOSFET. So because it's still a bipolar device, but the switching is going to be faster than the BJT. So large current handling capability, large voltage blocking. Again, since this is a transistor, it blocks positive voltages, fast switching, and fully controlled. So basically, this is the structure of the device. So I use the same sort of setup as a MOSFET to show that it's essentially the same device, except you'll see that here at the bottom, what has been done is that we've got doping. So we've got a P layer. So remember with the MOSFET, you didn't have this P layer down here. So what has basically been added is this P layer down here. And it's this P layer that is effectively making it, it's a PNP, but this is what basically is creating that bipolar behavior. So even the nomenclature has changed, that now we're using terms from both. So we've got a collector, we've got an emitter, and we've got a gate. So the control, you can see that the control is coming from a MOSFET. So you can see up here, the gate control. So we got rid of the base. So we don't have a base control. It's not current control, it's voltage controlled. And we said voltage control is easier than current control. So the control, the switching on and off is coming from a MOSFET. Then the other bit about current is coming from the BJT. So we've got a collector and an emitter. And then, so basically what we have is now, yes, I still have this channel, so I can have current. I switch it on, so have a large enough gate voltage, and then electrons will come from the emitter, which is actually this region down here, right? Then I create a channel so that electrons flow through that and down through the N, and then basically through this. So this has to also, we have to sort of, and then into the collector. So through this layer, and then it gets collected. So there's this other extra layer. So it's sort of behaving, like I said, it's got that sort of bipolar behavior. So these electrons go down here and then holes. So the holes are emitted. So you have electrons coming down and then holes going the other way. So I've got a bunch of holes. So actually that sort of show, the numbering sort of helps to explain what is happening. So I've got these holes coming down. As the holes come down, as the electrons come down, then I've got these holes. So the holes are the positive ones. So those ones will flow towards the emitter. So I've got bipolar current. So the current is being, the charges are basically being moved by holes and by holes and electrons. So it's a bipolar device. So I've got both. And so I can have a lot more current flowing because of that. So I have some current flowing through there. And then obviously I have some holes just that go directly, just directly like that. So, so the only real difference you can see is basically this other layer that we've added. So it actually has more layers. So this is actually 4 layers. You can sort of, it's kind of 4 layers in some places, although it's 3 layers in this side, but it's sort of 4 layers for this side. So that's what we have. So just got the MOSFET and added this layer to it. And that created basically this combination. So we're getting the benefits from BJT and from the MOSFET. Okay, so when we look at the IV characteristics, so the explanation of this is the reason I'm not spending any real time on it is because it's very similar. The only difference is this. Okay, so when we look at the IV characteristics, the IV characteristics are basically sort of similar to what we have with the BJT. So now we're calling this VCE and we're calling that IC. So collector current and then VCE. Again, we want to operate in the saturation region when it's on, because out here, the voltage will be small. The VCE saturation is small. So that product of VCE and a large IC will be a relatively small amount. And remember, that's the power that's being dissipated. So operate in the saturation or in the cutoff. Yes, Emilio.
There is something I was trying to analyze. In order to get you said we added the BJT and the MOSFET to get the IGBT.
Yes.
Then how come that the IGBT is only controlled by voltage, yet MOSFET, we said it is controlled by the voltage, because I remember the voltage VG, and the BJT is controlled by current. So if I add the current and voltage, why is this one only controlled by voltage, not both voltage and current?
Oh, yeah, so to start the process going, so to start this, so I start the process going by creating this channel. So I'm applying a voltage. So that voltage, basically, that large gate voltage will open up this channel. So that electrons can flow from this N plus region, we're now calling it an emitter, flow into, basically, they'll flow into the N region. So through that channel that we've created, then they'll be, so the VC is going to be a positive value. So we are pulling them this way. So as we pull the electrons down here, that automatically sort of emits holes. So it will get the holes emitted out of here. And then the holes will start basically the opposite direction. So they'll create, so we've got currents in sort of two ways. So part of it is going through this, and the other bit is going through now, okay, what is called number 2, I suppose. So, but to start off, I'm starting it off all with basically opening this channel, creating a channel. And so creating this channel is done using a gate. Okay, that makes sense. So to basically start it off, we are starting it off with this voltage and creating this channel. So once this channel is removed, all the current will stop flowing. So that's sort of the difference.
So there is no way we can start it with the current, since to get IGBT, we added the BJT and the MOSFET. And the BJT, we started with the current, and the MOSFET, we started with the voltage. I would expect, as in personally, that IGBT should either be started with the current or voltage, since it is a combination, or maybe it was fixed to only voltage.
Because the gate, so the control is done with this gate. So the emitter and collector are just that. So in theory, the emitter and collector are sort of like a wire through which the large amount of current will flow. But okay, so remember sort of the analogy I used for this. So remember, this is sort of, I've not done anything with IGBT. I didn't include it. That basically I want current flowing from the drain to the source. Oh, okay, so whatever it is, but the control, I'm controlling it with a gate. So one of the issues we want to get rid of, one of the problems we want to get rid of is the control. Current control is, so it's harder to drive these devices using current. So would prefer to have a system that is voltage controlled. So where we can switch a voltage on and off. Let's say on and off. So voltage control is better than current control. So by combining this, one of the things we really want to get rid of is current control. So we want the control to be with respect to current, we want to control it with voltage, not with current. So that's why we make sure that we don't control this with the current. That's why we don't want to do it that way. Okay, okay. So, and this is a benefit. Doing voltage control is a real benefit. So if I was comparing a MOSFET to a BJT, the drive system would be easier because I'm doing voltage control. I'm switching it on and off using a voltage. Okay, so so what we'll do is so this is a 2-hour one. So what I would want to do is, so we'll do this tomorrow. So we can tomorrow, the 2 hours are up. So tomorrow, what time is it's supposed to be at what, 2 p.m. tomorrow? I think it's 2 p.m. So we'll do this again at 2 p.m. because I want us to look at the thyristors. So tomorrow we'll look at the SCR. So we can do this in mole. So after that, then we can start looking at rectifiers. So tomorrow around, I think it's 2 p.m., 2 to 3 p.m. I think that's what's supposed to do. So we'll do another Zoom. Micah is still down, so I can't come to campus. So we'll do this again tomorrow. We'll do a Zoom tomorrow. So again, I'll send everything tomorrow. I'll send the link. It'll probably be a different link. So okay, see you tomorrow. Well, not see you, but hear from you tomorrow. So we'll have another Zoom meeting tomorrow. Okay.